This video is about waves and it comes up in the P1 paper. So try and think of as many waves as you can. I'll go through some now. So we have water waves that are classed as waves. You have sound waves, microwaves. Now any EM spectrum wave is a wave. Earthquakes, for example, seismic waves. Ultrasound is also a wave. Now the definition of a wave is that they are a series of oscillations or vibrations and they travel from one place to another, and when they do this they actually transfer energy from one place to another. This is a standard wave diagram. You need to know different parts of it. So these are called peaks or sometimes called crests, and at the bottom you have troughs. The wavelength is the distance on one point on a wave to the same place in another wave. So you can go peak to peak or trough to trough, but you can also go from here to here or here to here. I find it easier when doing it though to go from peak to peak, and then you don't get confused. It's measured in meters, as all distance and lengths are in physics, and the amplitude is the thing that people get mixed up with the most. It's not the whole length of the wave, it's the distance from the centre of the wave to the peak, or the distance from the centre to the trough. These are some definitions you need to know. So the amplitude is the maximum height of a wave measured from the middle. The wavelength is the shortest distance between a point on a wave and the same point on the next wave. And frequency, measured in hertz, is the number of waves passing a point per second. So say 2 waves per second would be a frequency of 2 hertz. So it says here a frequency of 6 hertz would mean that there's 6 waves passing a point every second. Now you might need to use the wave equation. This is given to you on the P1 formula sheet. So it is wave speed equals the frequency times the wave length. So speed is measured in meters per second. Frequency is in hertz. Make sure you put a capital H and a little z. Don't put a little h, you won't get the marks. And wavelength is in meters. On the formula sheet though, it will be given to you like this. V, which just stands for wave speed, equals f, the frequency, times the wavelength, which looks like this weird giraffe thing I always say it looks like. Here is a triangle. If you wanted to put it in the triangle and learn it, it would be V, F, and then lambda for the height, the distance, sorry. Wavelength. Here's an example. So Dylan is standing on the end of a pier. He measures the water waves going past him, as you do. The wavelength of each wave is 1.3 meters. It's got very good accurate calculations, it seems. He counts 2 waves every second. Find the wave speed. So I've highlighted here, and in the exam question you should underline it, the key points here. So if we were going to put it into the equation, it would be V equals 2 times 1.3, which is just 2.6 meters per second. Now there's different types of wave. You have transverse waves and longitudinal waves. They're both made up of oscillations, but they're ever so slightly different in the way that they transfer energy, and you need to know the differences. So the first one is a transverse wave. Now these actually go up and down like the standard wave. We say, and the word you need to use here is that the transverse waves have oscillations that are perpendicular, or you can say at right angles, to the direction of energy transfer. So you see the energy transfer is going this way, but the oscillations are going up and down, so they are at right angles. I have seen that asked in an exam before. So ripples in a pond would be transverse. Slinky or a mechanical wave could be transverse. You may have done this in class before. Other examples would be light, microwaves, X-rays. Like I said, any EM spectrum wave would be a transverse wave. Longitudinal waves are a little bit different. So they're like a series of vibrations. These require particles to travel through, unlike the transverse waves. So we say that in a longitudinal wave, the oscillations are to and fro along the same direction. So therefore they are parallel to the direction of energy transfer. And like I said, that's been asked before. And you have a series of compressions and rarefactions. The way I teach it is to think of a longitudinal wave like together, banging together, and it makes a sound. And I say transverse wave is like this. Now, longitudinal waves are sound. Ultrasound would be a longitudinal wave as well. And then some mechanical waves and one type of seismic wave. I have seen them in an exam ask for what wave could be both transverse and longitudinal. And the answer is mechanical, or they did accept the answer slinky. So don't be tricked out by that.